Okay, so here's the last thing that we were talking about last time. We were talking about suppose you've represented a linear transformation as a matrix. Reminder, if you represent a linear transformation as a matrix, what you're doing is you're choosing a basis with respect to which to talk about input vectors, a basis with respect to which to talk about output vectors, and effectively then you're describing the linear transformation T based on what does T do to input coordinates to give you output coordinates, all with respect to those chosen bases. Okay, so suppose that a la a diagram like this, you've represented a transformation with respect to one pair of bases, and then suppose that instead you would like to represent that same transformation just with respect to a different pair of bases. So, question, how do I turn this matrix into that matrix? That's the thing that we were talking about. And the big idea, I'll remind you, is that this matrix that you're interested in, that does that, right, it's a product. When you can see it right here, it's that first, followed by that second, followed by that third. Right? And this diagram, kind of a scary and imposing looking diagram, but ultimately it tells you exactly what to do to figure out how to use what you know about this orange matrix to determine what you would like, namely this green matrix. Okay. All right, so we talked about that last time, and that's about where we ended it. So I'd like to show you an example of this in action. Let me call your attention to a previous application that we wrote down. This is how to represent a linear transformation with respect to a basis, and we were talking about flipping over this line. Right? And the big idea that we had was, phooey on the standard basis. Let's represent it with respect to this other basis that we make up. Let's represent T with respect to a convenient basis. Because life is easier with respect to that convenient basis, and look how easy it was to write that down. I don't know how to write this with respect to the standard basis. It's easy with respect to this basis. And then I gave you all my little apology and said, okay, well, technically, okay, but if it does remain that I want to find T with respect to the standard basis, what do we do? And, well, we have the tools now. Here we understand T with respect to one pair of bases. I want to understand T with respect to a different pair of bases, namely the standard basis for both input and output. So what I need to finish up this example is to do a change of basis a la this to finish that last example. Okay, so there's a couple of examples that I have written out in detail here. I'm going to just do one of these. I'm going to do the second one actually, but I'll call your attention to what the first example asks, and that is suppose you want to find a matrix A that has the following two arithmetic properties: that you multiply by 1, 3, you get 2, 5. And furthermore, if you multiply by 2, 5, you get 1, 3. So how would you find such a matrix? And roughly speaking, we're going to take a point of view of clever use of bases to answer this question. I'm going to let you all read the details for that. It is highly analogous to what we're going to do in this second example. This one I am going to go through in detail. Okay. All right. So I would like to understand this matrix B, that when you multiply by 1, 3 gives you 3, 2, and when you multiply by 2, 5, you get 4, 3. And it's kind of a trick. How would you find such a matrix? By the way, let me recognize that there is a brute force way to solve this problem. The brute force way to solve it is to recognize that the matrix B is clearly 2 by 2. Therefore, it has 4 entries. And in fact, what I have here are a total of 4 equations involving those 4 unknown entries, and you could call this a 4 by 4 system and solve it. But that's a very brute force, blunt way to do it, and I would like to find a more clever way to do it, but also more to the point, I would like to show you how you can take advantage of change of basis in this context. Okay, all right. So, first thing to realize, don't think of B as just a matrix. Think of it as a way of representing a linear transformation. Let's think of this in more sophisticated terms. We're trying to find a linear transformation S. Let's call it. Specifically, I would like to understand S with respect to the standard basis. Okay, but as a first step in understanding S, let's ask, is there some other basis with respect to which S would be easier to understand? Kind of like what we did here. This linear transformation T was much easier to understand with respect to script V. The geometry of the situation happened to give me a strong motivation for what script V ought to be. So if I can first understand the linear transformation with respect to a different basis, then I do change a basis. So what would be a good choice of basis here, given that I'm trying to understand S as represented by B? Okay. Well, here's the thing. If I want to understand S, I'm going to need to know an input basis. How am I going to decide on what the input basis will be? Keep in mind what we'll do with the input basis. The input basis will be the vectors that I put in to the linear transformation. Well, there's a couple of vectors staring me right in the face that I already know how to put in to the linear transformation. I know what S does. Well, I know what B does. To 1, 3 and 2, 5. So that makes a good choice for my input basis, script V. We use that as our input basis, and remember, eventually, now we'll have to work out the details when we get down to it, but this input basis, those are the vectors that go in to S. Okay. All right, now, right. Next question. What should this output basis be? This output basis script W. Keep in mind what I'm going to do with script W. Script W is the basis with respect to which I need to understand these outputs. I'm going to need to write the coordinates of these outputs with respect to W. What are these outputs going to be, by the way? Well, we've already agreed that the inputs are 1, 3, and 2, 5. So those outputs are going to be 3, 2, and 4, 3. Now, I guess I could use the standard basis, but let's not. Can I think of a basis, a nice, convenient basis with respect to which 3, 2 and 4, 3 are easy to write? And how about 3, 2 and 4, 3? Don't be ashamed of making your life simple. Right? These output vectors 3, 2, and 4, 3 make a fantastic basis with respect to which to understand themselves 3, 2, and 4, 3. Okay. All right. So we make those choices for our input basis and our output basis. I then understand these columns one at a time. So these are our output vectors, W1 and W2. Let's talk about this first column. How do I get this first column? The first column comes from that equation, or more specifically, I need to understand S of V1, coordinates with respect to script W. That's the formula for the first column. And I know S of V1 is W1, and W1, how do I write W1 as a linear combination of W1 and W2? Well, 1, 0. Super easy linear combination. Super easy because I set it up this way, right? I conveniently set up my input script V basis to be something where it'll be easy for me to compute what the linear transformation does. And then I chose my output basis to be something with respect to which W1 would be easy to write down. So this was a rigged game. I rigged it, right? I rigged it to make my life easy. Okay, likewise, now let's look at the second column. Where does the second column come from? Well, ultimately it comes from this equation. More specifically, it comes from understanding what is S of V2 with respect to the script W basis. Right, this is the formula for how I compute the second column. Well, I've arranged it for S of V2 to be something that I know. It's W2. And I've furthermore arranged for that thing, W2, to be easy to understand with respect to the script W basis. W2 is 0 W1 plus 1 W2, and thus this second column is 0, 1. Everybody on board? Okay, so reminder, just like this old example, step 1, understand the linear transformation with respect to whatever basis makes your life easier. Here, geometry gave us a suggestion of a really convenient choice of basis. Right? Here, it wasn't geometry exactly, but it was, the givens of the question. The givens of the question up here strongly suggest an input basis and an output basis. We write what we want to know, or we write what we can about S based on those choices, and now what we have left over is just a change. Sorry, my button's not working. There we go. Just a change of basis problem. I have. Hit the wrong button again. Hang on. Here we go. I have S with respect to my chosen bases. I want S with respect to the given bases, standard basis. And I convert by this formula over here that the matrix I want is this product like this. Oh gosh. Just like we talked about a few minutes ago. And that's what we have here. Change of basis matrix from W to S is how we end it. Change of basis matrix from S to V is how we start it. We have formulas for how to write down change of basis matrices. We talked about those last time. I'll let y'all persuade yourselves of those here and here. And now it's just an arithmetic problem, right? So this matrix here, the orange one, easy because we were clever. Then the matrix that we wanted to find falls down to just arithmetic. Okay. How we doing? Questions? Everybody see the strategy there? So, reminder, I want you all to read through this previous example that's similar. It's very similar, of course. And you've got to think to yourself, what would be a good choice of input basis? What would be a good choice of output basis? What I did here is choose a single basis. Just V1 and V2. Just this vector and that vector. So it makes things go through just a slightly differently, but it still works out really nicely. Okay. All right. Okay. Moving along. We start a new section today, 5.4, Eigenvalues and Eigenvectors. By the way, this section is going to look very different from section 5.3. It's going to not be at all clear, in fact, as we're going through 5.4. What does this have to do with 5.3? 5.3 is all about, roughly speaking, change of basis and representing things with respect to bases. Here we're just going to be looking at, just matrices and certain cute coincidences that happen with matrices. No clear connection. It's going to turn out, we're going to see this very soon in section 5.5, that actually there is a very strong connection between what we're doing here with eigenvectors and eigenvalues and what we were doing in section 5.3 with change of basis. I just wanted to foreshadow that a little bit. We don't really quite have the tools to see where that's going to come from. Ultimately, though, and we'll see this once we get to chapter 6, very hard to see this coming, but ultimately, this is one of the big ideas that will let us solve a bunch of differential equations as it happens. So anyway, again, just a little foreshadowing. Here's the basics of eigenvectors and eigenvalues. An eigenvector, given a matrix, here let me start with that. Given a matrix, by the way, a square matrix. An eigenvector is a vector such that when you multiply by that matrix, you get a scalar multiple of that exact same vector. So that's what an eigenvector is. It's a weird kind of coincidence, you might say. Certainly this doesn't happen often, right? I mean, y'all have got a lot of experience with taking a matrix and multiplying it by a vector, and you get some totally different direction vector most of the time. I mean, just it seems weird that you would get something that's exactly in the same direction. It's more than a curiosity when this happens. This turns out to be powerfully important. Again, it's going to have to wait for a little while before we can see why that is. So we're going to study eigenvectors in anticipation of all these great applications that will come later. For the moment, we're just going to think of it as a kind of a weird coincidence. The scalar in that coincidence is called the eigenvalue. So that's all eigenvectors and eigenvalues are. It's kind of a letdown, really. I remember when I was first approaching this subject, and I remember being all prepared for some sophisticated, eigenvector, that sounds hard, right? And let's consider this to be kind of a letdown. It's such a kind of simple concept, really. Anyway. Okay. A couple of little details. One is eigenvectors do have to be not zero. And the reason for this is the question just becomes kind of silly if you think about it. The zero vector, any matrix times the zero vector will give you 0, which of course is always constant times the zero vector. It's just always going to work. But even worse than that, 0, if you were to think of it as an eigenvector, every real number would be an eigenvalue. And it's just very anomalous and weird, and so we do throw in this requirement. When we talk about eigenvectors, what we mean is a non-zero vector that has this property. Okay. Alrighty. Also, just a quick cultural point. This construction here, this verbal construction of putting this prefix eigen in front of stuff. People have taken it and run with it. So it turns out there are many other situations kind of like this, where maybe instead of multiplying a matrix times a vector, maybe you're applying a linear transformation. One of those ones that isn't a matrix. Applying a linear transformation to a vector. Or maybe you're writing down certain kinds of differential equations. Or maybe you're doing quantum mechanics and you're looking for functions that satisfy Schrodinger's equation. Various different situations, the mathematical circumstances you can be interested in that end up, as it turns out, algebraically looking a lot like that equation. And the resulting things, the resulting solutions, they'll just take eigen as a prefix and sort of stick it in front of there. So an eigenfunction is a function that satisfies an equation along these lines. An eigenstate is a quantum state that satisfies Schrodinger's equation, which actually looks a lot like that in certain circumstances. Okay. So anyway, you'll see in your future engineering work various constructions of this sort where you have eigen something. All they're saying is something's going on that's kind of like that. All right. Okay. How do you do it? How do you find eigenvectors? How do you find the vectors? How do you find the eigenvalues as well? There's a little clever algorithm. It's mostly just a matter of following the algorithm. Let me explain the thought process. First, note that equation is equivalent to that equation. You can imagine an extra factor of the matrix I sitting in there right there. And if you take this term and move it around to the other side, there's your A minus lambda I. So these two equations are equivalent. Why would we do such a thing? Why do we care? Well, this equation is something that I've got previous experience with. Notice, equals 0. So we're looking here for vectors that are homogeneous solutions, and we know how to do that. Right? We've got a lot of experience with it. Finding a null space, another way to say the same thing. Okay, now, yeah, but what's lambda? If I'm going to try to find these eigenvectors, I need to row reduce A minus lambda I. What's lambda? Don't know it yet. Right? So here's the next clever observation. Do keep in mind eigenvectors are non-zero. Right? So let's look at this equation again that I have circled in blue. That equation says A minus lambda I is a matrix with a non-trivial null space vector. Said differently, the dimension of the null space is greater than 0. There's a long list of equivalent conditions that we wrote down at the end of chapter 2 of different ways to think about singular and non-singular matrices. Right? I think I wrote the list down with respect to non-singular matrices. Long list of equivalent conditions. Punchline, if a matrix has a non-trivial null space, that matrix is singular. And also on that list, if a matrix is singular, its determinant is equal to 0. And this actually is a really good way to find eigenvalues because notice that this expression, determinant of A minus lambda I, that's a polynomial involving lambda. I appeal to your algebraic intuition. If you take a matrix full of numbers and you subtract lambda from the diagonal entries where the identity has a 1, right? You've got a matrix with a bunch of lambdas in it. When you take the determinant, you're going to multiply a bunch of those terms by a bunch of those other terms. You'll be multiplying a bunch of factors of lambda. You will end up with a polynomial. Great big monster, polynomial, nevertheless a polynomial in lambda. And so we need to find the roots of that polynomial. Roots of the polynomial, values of lambda that give you 0, right? Those values of lambda are your eigenvalues. So this is the process. The process is, given a matrix A, step 1, write down the characteristic polynomial. Step 2, find its roots. Find these values of lambda that make the polynomial 0. Once you know those eigenvalues, you plug into there, and the eigenvectors are just the null space of that resulting matrix. That's the game. Let's get our hands dirty and do one. Here we go. Start off with this matrix here, which I, by the way, took directly out of the book. So let's take that matrix and go through the process. Step 1, A minus lambda I. Okay, A. Here are those numbers. There's the A. Minus lambda I. Well, keep in mind, I is the identity matrix. There's ones just along the diagonal. Multiply by lambda. Now you have lambdas along the diagonal. When you subtract, you get this. So there's A minus lambda I. The characteristic polynomial is that determinant, which you multiply out, collect all the terms, factor. Now I just skipped over a bunch of algebra. Make sure that you can do all that algebra, computing the determinant, multiplying, collecting, factoring. Right? So there's our characteristic polynomial. The roots of the characteristic polynomial are the eigenvalues. So solve for lambda. You get these numbers, -1 and 4. Those are the eigenvalues. And with those eigenvalues, we can find eigenvectors by computing null spaces. And we'll do that in just a second. But before I get into computing those null spaces, let me take a quick pause. Is everybody happy with how I got these eigenvalues? Okay. Right. Okay. Okay, we have to take these one at a time. Reminder, once you have the eigenvalues, right? Once you have the eigenvalues, then you find the eigenvectors by finding the corresponding null space of A minus lambda I. Okay, so here we go. starting with our first eigenvalue here, -1. Plug in lambda equals -1. Write down the corresponding a minus lambda I. There you go. There's your null space equation. The eigenvectors that we are looking for are these null space vectors. And y'all got techniques, right? You can, for one thing, you can take that matrix and row reduce. Right? Go through the whole row reduction process and solve for your pivot variables in terms of your free variables. You know, the usual thing. And there's all your eigenvectors. By the way, notice that the eigenvectors, in being a null space, are a subspace, and therefore all multiples of any eigenvector also an eigenvector. Yeah, everybody good? Everybody good so far? Okay. I want to show you all a shortcut. I like this a lot. The book doesn't mention it. I think this is a really nice way to avoid calculation, though. Not that this row reduction is all that bad, but still, wouldn't it be nice if we could streamline this process a little bit? There's a really nice way to streamline this. Here it goes. There again is this 2x2 system that we need to find the null space of. And let's ask the plausible question, looking at that matrix, what is its rank? Flashbacks to chapter 2, right? We haven't thought about chapter 2 in a while. All that. Excuse me, chapter 1. This goes way back. So what's the rank of this matrix? Don't forget the rank is the number of pivots in the reduced echelon form. So once you row reduce, how many pivots would there be? But the rank, we also know other things about it. The rank is the dimension of the column space. It's the dimension of the row space. And it satisfies this cool theorem called the rank nullity theorem. So the dimension of the null space plus the rank gives you the number of columns. Various things we know about rank. So what do I know about the rank of this matrix? Well, process of elimination, I know the rank has to be 1. And this is an easy process of elimination. This rank can't be 2. No way. I already know that a minus lambda I is singular. That's the whole sort of strategy here, is to find a matrix a minus lambda I that when you have an eigenvalue, as we do here, makes this thing singular. Right? We've rigged it up so that a minus lambda I would be singular. If it's singular, it's missing at least one pivot. So the rank can't be 2. The rank also can't be 0. This is a kind of silly observation, but it can't be 0 because if there's 0, there's no pivots. If there's no pivots, that means the reduced echelon form doesn't have any first non-zero entries in any rows. That means the reduced echelon form is all zeros. That would mean the original matrix is all zeros. That's by casual inspection obviously not true. Yeah. So the rank, not clear yet why we are so excited about this, but the rank can't be 2, can't be 0, therefore it has to be 1. This matrix has rank 1. Now, why do I care about that? Well, keep in mind what we're interested in. We're interested in the null space. The rank nullity theorem tells me that the dimension of the null space is the number of columns minus the rank. So the number of columns is obviously 2. Process of elimination, the rank was 1. Therefore, this null space that I'm looking for is one-dimensional. Now, again, still not 100% clear why we would care about this. I mean, how is this going to save us trouble? The reason this saves us trouble is because knowing that it's a one-dimensional vector space, we can take advantage of wonderful features of one-dimensional vector spaces. Here is a wonderful feature of a one-dimensional vector space. A basis for it consists of any one vector. Right? Any non-zero vector in that one-dimensional vector space is immediately a basis. That's just a peculiarity, right, of one-dimensional vector spaces. So rather than okay, I've got to go through a whole row reduction to find the null space, and I've got to do the row reduction because it's the only way that I know with confidence that I will get all of those solutions and I won't get any bogus solutions. It's the one reliable means that I have of finding that null space. No, now, the problem has resolved down to just find any vector in the null space and you're good. Any solution will do. Knowing that the dimension is 1, any solution that you find is a basis, and therefore the null space that you're looking for is all multiples of it. And so we're done. Yep.
So because there's only, since it's one dimensional, there's only one solution for a basis.
Yeah.
If you plugged in 4 as the lambda value, would you get a multiple of?
Oh, then there'll be it's a slightly different story for that. So for the different eigenvalue, you're going to have a different matrix. A minus lambda I is going to be different, and we'll talk about that next. Yeah. Okay. By the way, how did I get this one solution? This 3, 2. How did I see that works? Really, just kind of smart alecky observation. I'm looking at the 2 and the 3 and the minus sign. And clever observation that if you multiply the 2 by a 3 and the 3 by a 2, right, the products are the same and the minus sign makes them cancel and yay, it worked. I mean, it's nothing sophisticated, and there's usually some way, certainly in cases where it's two-dimensional, to eyeball a solution. So there you go. This is your alternative to doing a row reduction. Now, you will notice that there is an entire page of discussion here. Most of this discussion is to help y'all with your first time through this argument, right? I don't expect you to write anything resembling this much on an exam if you make this argument. On an exam, if you want to apply this method, all you have to write down, as far as I'm concerned, is rank equals 1, dimension of the null space is 2 minus 1, therefore solution. Just what I have circled there is fine. Because everything else is pretty clear. I mean, when you write down the rank as 1, it was obviously because you've eliminated 2 and 0, and you've eliminated those for the same reason that they are always eliminated. Right? Can't be maximal rank, and it can't be 0. Here you're clearly communicating your understanding of the rank nullity theorem. And one-dimensional vector spaces really are pretty easy. Certainly, this late in the course, I'm comfortable with you just writing down just these things. So I hope you'll consider that as an alternative to row reductions in cases like this. And we'll see another example of this in a few minutes, this kind of thing. Okay, moving along. So the question was asked, here we were considering this eigenvalue of -1. What about this eigenvalue of 4? Same deal. For that eigenvalue of 4, let me zoom back in. For that eigenvalue of 4, plug that in to there. Here's your new equation. And again, you can row reduce to find the eigenvectors. Or you can make another rank argument, which is what I encourage. Looking at this matrix. Gosh, let's see here. Sorry. Looking at this matrix here. That matrix, the rank is obviously not 2. It's singular. It's A minus lambda I, which has got to be singular. So clearly it's not 2. The rank can't be 0. That'd be silly. So the rank's got to be 1. Therefore, the dimension of the null space is 2 minus 1, which is 1. Therefore, we're looking for a one-dimensional vector space. Smart alecky observation. -1 works, and we're done. Not that a row reduction would be hard either, but still, I think this is nice. Okay. Pause. Questions? Okay, so let me talk to you a little bit about terminology. Let's look at, for this eigenvalue, we found these eigenvectors. And I would like to address the question, how many eigenvectors did we just find? And I'm going to first tell you the strict answer to the question, and then I'm going to tell you how people talk. Ultimately, I'm going to be describing what I like to think of as math slang here. There's a sloppiness of how people talk about the answer to this question that's nevertheless very convenient. So, to the question, how many eigenvectors did we just find? Well, keep in mind, my clever observation was just this one vector, but all multiples of it, of course, because the collection of eigenvectors is a subspace, and therefore all multiples are going to work too. I have actually found infinitely many eigenvectors. Yeah? Right? Everybody see that? That's, yeah.
Can K be negative?
Yeah, sure. No problem. Absolutely. K can be positive, negative, whatever. Can't be zero, technically, because, yeah. Right. Okay, so I found infinitely many eigenvectors. Here's the disappointing thing about that answer. Anytime I have an eigenvalue, I will find infinitely many eigenvectors. Right? So this handy terminology of, hey, how many eigenvectors did you find, is kind of wasted with the answer being, well, infinity, of course. Right? It's the answer is always the same, right? Okay. Here, though, is a similar question that does not always have the same answer, and that would be very nice to be able to talk about more conveniently. And the question would be, how many eigenvectors are in a basis for the collection of eigenvectors that I just found? Okay, so what's the dimension of this vector space of eigenvectors? Gosh, there's a lot of words in all these constructions. So here, how many vectors are in a basis of what I've just found? Well, one. But you can imagine some other scenario, bigger matrix, different story. You could imagine that a null space of A minus lambda I might be 2-dimensional or 5-dimensional or what have you. So how many eigenvectors are in your basis is an interesting question. And we're going to find as we go further along that it's a very interesting question that's we're going to need to talk about a lot. And rather than talk about how many vectors are in a basis for my collection of eigenvectors, what people say, with the understanding that of course that's what I meant, is how many eigenvectors did you find? Right? So in common parlance, and again, this is math slang, it's sloppy, but everybody knows what you're talking about, is to say we found one eigenvector. With the understanding that, of course, what that means is we found a collection of eigenvectors with a basis consisting of one eigenvector. Everybody see what I'm talking about here? So just be aware of the sloppiness of, and yet very common pervasiveness of this language. People are going to say, I found one eigenvector. Don't misinterpret what they're saying. Of course, strictly speaking, you always find infinitely many eigenvectors. But again, that's just not what people mean. Okay. All right. So grand total then for this matrix that we started off with, for this first eigenvalue, we found one eigenvector in the way people talk. And for the second eigenvalue, I found one eigenvector. So grand total, we have found two eigenvectors. Yeah? Everybody good? Okay. So let me remind you of something from a long time ago. This goes all the way back to chapter 4. Do y'all remember this business with, when we were looking for, we had a constant coefficient linear equation, homogeneous, and we were looking for solutions to the differential equation, and we wrote down something called a characteristic polynomial. And by the way, weird, this thing here, we have called a characteristic polynomial. So first of all, that's uncomfortable. We have now used the term characteristic polynomial for two very different things. On the one hand, the characteristic polynomial of a matrix is this thing. On the other hand, the characteristic polynomial of a differential equation was that other thing from long ago. Totally different things. Good news, there's never any confusion. Characteristic polynomial of a matrix, well, a matrix is simply not a differential equation. So when you say characteristic polynomial of a matrix, it's perfectly clear you mean this one, not the other one. That wouldn't have made any sense at all. Okay, nevertheless, these two polynomials play kind of analogous roles. Let's think about, way back when, what did characteristic polynomials do? Characteristic polynomials had the feature that if you find a root, if you can find a value of lambda, let's do it like this. If you can find a value of lambda that makes that 0, then what you have is a solution to your differential equation. So the characteristic polynomial had roots that give you solutions. And notice that same thing is happening over here with this brand new characteristic polynomial. This characteristic polynomial has roots that, by way of, once you have that, then you put that here, and then you row reduce to find the vectors, give you the things that you're looking for. So the shared term characteristic polynomial kind of makes sense in the sense that it's, in both cases, it's a polynomial whose roots tell you what you want to know. So there's that. Okay. All right, so here's another thing I want to talk about, going back to this page here. There were some happy coincidences that we found in Chapter 4. When you're looking at a constant coefficient linear equation that has a certain order, the characteristic polynomial has the same degree and the same number of roots, which gives you the same number of then solutions. All these numbers are always the same. And because of theorems that we have, the number of solutions that you need is always the same as that too. So everything just fits. Everything's perfect. If you have an nth order equation, then everything else, all your other counts are also in. How many solutions are you going to find? What's the degree of your polynomial? How many roots did you get? What's the dimension of the thing you're looking for? All of those also in. Wonderfully happy coincidences. And now check this out. What has happened in this example here? We started off with a 2x2 matrix that ended up with a degree 2 characteristic polynomial, thus giving us 2 roots, aka eigenvalues, and in the sloppy language of how people talk, 2 eigenvectors. And there is a strong lure to wanting to say, oh, this is unfolding just like it did in Chapter 4. Characteristic polynomial, the roots give us the things we're looking for, and fundamental theorem of algebra, the number of solutions is always going to be blah blah blah, and it seems like it ought to work out. The reason I'm making a big deal out of this is so that you will not buy into that. This is an illusion. This is a coincidence that happened in this case, and it's not a rare coincidence. This will happen very often. But unlike in Chapter 4, where everything just worked out, not so when you're talking about matrices and eigenvectors. And I wish it were, but it just isn't. By the way, it's not that we just haven't found the right eigenvectors yet. It's that they aren't there. So it is not the case that you'll always find the, what you might call expected number of eigenvectors. Here's an easy counterexample. Look at that unimposing matrix. Seemingly harmless. Ones and zeros, right? What could possibly go wrong? This is a terrible matrix. In a very meaningful way. So play the game. There's a characteristic polynomial. Multiply it out, factor it. You get this. Therefore, 1 root. Therefore, 1 eigenvalue. And if you take that 1 eigenvalue and write down the equation to find the eigenvectors, there it is. You get 1 eigenvector. End of story. There is no hidden eigenvector that we'll find elsewhere. Right? It's just not there. So this is a big disappointment. This is going to cause serious problems for us later on when we're solving differential equations. This is a bummer. There are just not as many eigenvectors as you would hope in general. Okay. Let's see here. In the interest of time, let me. I guess I'd better do this one last. Yeah. Okay. This is good. Let's do this. Just another example. But here's a matrix. Characteristic polynomial factored eigenvalues. That's just algebra. Y'all can do that. Okay. But let's talk through the different ways that these calculations might work out. Let's look at that first eigenvalue. Your A minus lambda I equation turns into this. How do you make the rank argument for this matrix? It's a little different because it's 3 by 3. But again, there's kind of a process of elimination. And just think about what you know about the matrix. The rank can't be 3. We know it's singular. It's A minus lambda I. It's got to be singular. The rank can't be 3. Rank's obviously not 0. It means the rank is either 1 or 2. And how do you decide if it's 1 or 2? We do have to decide there. In this case, what I would encourage you to do is look at the columns. Specifically, look at these second 2 columns, the last 2 columns. These 2 columns are obviously not multiples of each other. So you immediately know the column space is 2-dimensional, therefore the rank is 2. Everybody on board? If the rank is 2, 3 minus 2 gives you 1. The null space is 1-dimensional. And again, be clever, and you can persuade yourself that this is a free and easy to observe null space vector. Since it's 1-dimensional, it's the only null space vector. Again, with all multiples of it, of course. So anyway, slightly different twist of the algebra. What about for the other eigenvalue of -1? Here's what you've got. Let's think about this matrix. In this case, the row space is a natural thing to look at. There is one non-zero row vector, therefore the span of the row vector is clearly 1-dimensional. The rank is therefore 1. That means that the null space is 2-dimensional. This is kind of bad news. 2-dimensional vector spaces are not as awesome as 1-dimensional. 1-dimensional vector spaces are super, right? Just find a vector, you're done. It's all multiple. Any non-zero vector, you're good, right? That's fantastic. 2-dimensional, yeah, it's not quite as good, but 2 is still a good number. 2 has the nice feature that all you have to find are any 2 vectors that are not multiples of each other. Simply by virtue of not being multiples of each other, you know that these are independent and therefore a basis for your null space. How do you find these vectors? Again, just smart alecky observations. For this first vector, I look at the 3 and the -1. And I think to myself, well, 3 and -1. How about I multiply this one by 1 and that one by 3, and then they cancel. Right? Purely smart alecky observation. There's nothing deep going on there. Likewise, how did I find this vector? Well, I looked at these 2 numbers. And I say, hey, these are negatives of each other. Let's capitalize on that. So, a couple of smart alecky observations. Observe that you have found 2 null space vectors in a 2-dimensional null space. Declare victory. Okay. Okay, let's see, I've got 20 seconds. Yeah, okay, a little bit of terminology here. A little bit more terminology. This is really just a summary. Eigenvalues are roots of the characteristic polynomial. Eigenvectors are null space vectors. And I'll introduce this new term and call it a day. An eigenspace is just an easy way to talk about the vector space containing all the eigenvectors, namely the null space of A minus lambda I. All of that's a lot of verb. It's just a lot easier to say the word eigenspace, and we use this notation. Y'all have a great day. See you. We'll pick up here next time.